A self-replicating machine is a type of autonomous robot that is capable of reproducing itself autonomously using raw materials found in the environment, thus exhibiting self-replication in a way analogous to that found in nature. The concept of self-replicating machines has been advanced and examined by Homer Jacobsen, Edward F. Moore, Freeman Dyson, John von Neumann, and in more recent times by K.Eric Drexler in his book on nanotechnology, Engines of Creation, and by Robert Freitas and Ralph Merkle in the review Kinematic Self-Replicating Machines, which provided the first comprehensive analysis of the entire replicator design space. The future development of such technology is an integral part of several plans involving the mining of moons and asteroid belts for ore and other materials, the creation of lunar factories, and even the construction of solar power satellites in space. The possibly misnamed von Neumann probe is one theoretical example of such a machine. Von Neumann also worked on what he called the universal constructor, a self-replicating machine that would operate in a cellular automata environment. A self-replicating machine is an artificial self-replicating system that relies on conventional large-scale technology and automation. Certain idiosyncratic terms are occasionally found in the literature. For example, the term clanking replicator was once used by Drexler to distinguish macro-scale replicating systems from the microscopic nanorobots or assemblers that nanotechnology may make possible, but the term is informal and is rarely used by others in popular or technical discussions. Replicators have also been called von Neumann machines, after John von Neumann, who first rigorously studied the idea. However, the term von Neumann machine is less specific and also refers to a completely unrelated computer architecture that von Neumann proposed, and so its use is discouraged where accuracy is important. Von Neumann himself used the term universal constructor to describe such self-replicating machines. Historians of machine tools, even before the numerical control era, sometimes figuratively said that machine tools were a unique class of machines because they have the ability to reproduce themselves by copying all of the parts. Implicit in these discussions is that a human would direct the cutting processes and would then be assembling the parts. The same is true for repraps, which are another class of machines sometimes mentioned in reference to such non-autonomous self-replication. In contrast, machines that are truly autonomously self-replicating are the main subject discussed here. History. The general concept of artificial machines capable of producing copies of themselves dates back at least several hundred years. An early reference is an anecdote regarding the philosopher René Descartes, who suggested to Queen Christina of Sweden that the human body could be regarded as a machine. She responded by pointing to a clock and ordering, "See to it that it reproduces offspring." Several other variations on this anecdotal response also exist. Samuel Butler proposed in his 1872 novel Arraphon that machines were already capable of reproducing themselves, but it was man who made them do so, and added that machines which reproduce machinery do not reproduce machines after their own kind. In 1802, William Paley formulated the first known teleological argument depicting machines producing other machines, suggesting that the question of who originally made a watch was rendered moot if it were demonstrated that the watch was able to manufacture a copy of itself. Scientific study of self-reproducing machines was anticipated by John Bernal as early as 1929 and by mathematicians such as Stephen Kleene, who began developing recursion theory in the 1930s. Much of this latter work was motivated by interest in information processing and algorithms rather than physical implementation of such a system. However, Von Neumann's kinematic model, a detailed conceptual proposal for a physical non-biological self-replicating system, was first put forward by mathematician John von Neumann in lectures delivered in 1948 and 1949, when he proposed a kinematic self-reproducing automaton model as a thought experiment. Von Neumann's concept of a physical self-replicating machine was dealt with only abstractly, with the hypothetical machine using a C or stockroom of spare parts as its source of raw materials. The machine had a program stored on a memory tape that directed it to retrieve parts from this C using a manipulator, assemble them into a duplicate of itself, and then copy the contents of its memory tape into the empty duplicates. The machine was envisioned as consisting of as few as 8 different types of components, 4 logic elements that send and receive stimuli, and 4 mechanical elements used to provide a structural skeleton and mobility. While qualitatively sound, von Neumann was evidently dissatisfied with this model of a self-replicating machine due to the difficulty of analyzing it with mathematical rigor. He went on to instead develop an even more abstract model self-replicator based on cellular automata. His original kinematic concept remained obscure until it was popularized in a 1955 issue of Scientific American. Moore's Artificial Living Plants. In 1956, mathematician Edward F. Moore proposed the first known suggestion for a practical real-world self-replicating machine, also published in Scientific American. Moore's artificial living plants were proposed as machines able to use air, water and soil as sources of raw materials and to draw its energy from sunlight via a solar battery or a steam engine. He chose the seashore as an initial habitat for such machines, giving them easy access to the chemicals in seawater, and suggested that later generations of the machine could be designed to float freely on the ocean's surface as self-replicating factory barges, or to be placed in barren desert terrain that was otherwise useless for industrial purposes. The self-replicators would be harvested for the component parts to be used by humanity in other non-replicating machines. Dyson's replicating systems. The next major development of the concept of self-replicating machines was a series of thought experiments proposed by physicist Freeman Dyson in his 1970 Van Uxem lecture. He proposed 3 large-scale applications of machine replicators. First was to send a self-replicating system to Saturn's moon Enceladus, which in addition to producing copies of itself would also be programmed to manufacture and launch solar sail-propelled cargo spacecraft. These spacecraft would carry blocks of Enceladine ice to Mars, where they would be used to terraform the planet. His second proposal was a solar-powered factory system designed for a terrestrial desert environment, and his third was an industrial development kit based on this replicator that could be sold to developing countries to provide them with as much industrial capacity as desired. When Dyson revised and reprinted his lecture in 1979, he added proposals for a modified version of Moore's seagoing artificial living plants that was designed to distill and store fresh water for human use, and the Astro Chicken, advanced automation for space missions in 1980, inspired by a 1979 New Directions workshop held at Woods Hole. NASA conducted a joint summer study with ASE entitled Advanced Automation for Space Missions to produce a detailed proposal for self-replicating factories to develop lunar resources without requiring additional launchers or human workers on site. The study was conducted at Santa Clara University and ran from June 23 to August 29, with the final report published in 1982. The proposed system would have been capable of exponentially increasing productive capacity, and the design could be modified to build self-replicating probes to explore the galaxy. The reference design included small computer-controlled electric carts running on rails inside the factory, mobile paving machines that used large parabolic mirrors to focus sunlight on lunar regolith to melt and sinter it into a hard surface suitable for building on, and robotic front-end loaders for strip mining. Raw lunar regolith would be refined by a variety of techniques, primarily hydrofluoric acid leaching. Large transports with a variety of manipulate arms and tools were proposed as the constructors that would put together new factories from parts and assemblies produced by its parent. Power would be provided by a canopy of solar cells supported on pillars. The other machinery would be placed under the canopy. A casting robot would use sculpting tools and templates to make plaster molds. Plaster was selected because the molds are easy to make, can make precise parts with good surface finishes, and the plaster can be easily recycled afterward using an oven to bake the water back out. The robot would then cast most of the parts either from non-conductive molten rocky purified metals. A carbon dioxide laser cutting and welding system was also included. A more speculative, more complex microchip fabricator was specified to produce the computer and electronic systems, but the designers also said that it might prove practical to ship the chips from Earth as if they were vitamins. A 2004 study supported by NASA's Institute for Advanced Concepts took this idea further. Some experts are beginning to consider self-replicating machines for asteroid mining. Much of the design study was concerned with a simple, flexible chemical system for processing the ores, and the differences between the ratio of elements needed by the replicator and the ratios available in lunar regolith. The element that most limited the growth rate was chlorine, needed to process regolith for aluminium. Chlorine is very rare in lunar regolith. Lackner Vent-Torkson replicators. In 1995, inspired by Dyson's 1970 suggestion of seeding uninhabited deserts on Earth with self-replicating machines for industrial development, Klaus Lackner and Christopher Vent developed a more detailed outline for such a system. They proposed a colony of cooperating mobile robots 10 to 30 centimeters in size running on a grid of electrified ceramic tracks for round stationary manufacturing equipment and fields of solar cells. The proposal didn't include a complete analysis of the system's material requirements, but described a novel method for extracting the 10 most common chemical elements found in raw desert topsoil using a high-temperature, carbothermic process. This proposal was popularized in Discover magazine, featuring solar-powered desalination equipment used to irrigate the desert in which the system was based. They named the machines auxons, from the Greek word aukin, which means to grow. Recent work. Self-replicating rapid prototypers. Early experimentation with rapid prototyping in 1997 to 2000 was not expressly oriented toward reproducing rapid prototyping systems themselves, but rather extended simulated evolutionary robotics techniques into the physical world. Later developments in rapid prototyping have given the process the ability to produce a wide variety of electronic and mechanical components, making this a rapidly developing frontier in self-replicating system research. In 1998, Chris Phoenix informally outlined a design for a hydraulically powered replicator a few cubic feet in volume that used ultraviolet light to obscure soft plastic feedstock and a fluidic logic control system, but didn't address most of the details of assembly procedures, error rates, or machining tolerances. In 2005, Adrian Bowyer of the University of Bath started the Reprap project to develop a rapid prototyping machine which would be able to manufacture some, or most of its own components, making such machines cheap enough for people to buy and use in their homes. The project is releasing its designs and control programs under the GNU GPL. The Reprap approach uses fused deposition modeling to manufacture plastic components, possibly incorporating conductive pathways for circuitry. Other components, such as steel rods, nuts and bolts, motors and separate electronic components, would be supplied externally. In 2006, the project produced a basic functional prototype, and in May 2008 the machine succeeded in producing all of the plastic parts required to make a child machine. Some researchers have proposed a microfactory of specialized machines that support recursion. Nearly all of the parts of all of the machines in the factory can be manufactured by the factory. NIAC studies on self-replicating systems. In the spirit of the 1980 Advanced Automation for Space Missions study, the NASA Institute for Advanced Concepts began several studies of self-replicating system design in 2002 and 2003. 4 Phase 1 grants were awarded: Hodlipson, autonomous self-extending machines for accelerating space exploration; Gregory Chirikian, architecture for unmanned self-replicating lunar factories; Paul Todd, robotic lunar ecopoiesis; Tihama Tothfayil, modeling kinematic cellular automata, an approach to self-replication. The study concluded that complexity of the development was equal to that of a Pentium 4, and promoted a design based on cellular automata. Cornell University's Self-Assembler. In 2005, a team of researchers at Cornell University, including Hodlipson, implemented a self-assembling machine. The machine is composed of a tower of 4 articulated cubes, known as molecubes, which can revolve about a triagonal. This enables the tower to function as a robotic arm, collecting nearby molecubes and assembling them into a copy of itself. The arm is directed by a computer program, which is contained within each molecube, analogous to how each animal cell contains an entire copy of its DNA. However, the machine cannot manufacture individual molecubes, nor do they occur naturally, so its status as a self-replicator is debatable. New York University Artificial Neonatal Motifs. In 2011, a team of scientists at New York University created a structure called BTX based around 3 double helix molecules, each made from a short strand of DNA, treating each group of 3 double helices as a code letter. They can build up self-replicating structures that encode large quantities of information. Self-replication of magnetic polymers. In 2001, Jarl Breivik at University of Oslo created a system of magnetic building blocks, which in response to temperature fluctuations, spontaneously form self-replicating polymers. Self-replication of neural circuits. In 1968, Zelig Harris wrote that the meta-language is in the language, suggesting that self-replication is part of language. In 1977, Niklaus Wirth formalized this proposition by publishing a self-replicating deterministic context-free grammar, adding to it probabilities. Bertrand du Castel published in 2015 a self-replicating stochastic grammar and presented a mapping of that grammar to neural networks, thereby presenting a model for a self-replicating neural circuit. Partial construction. Partial construction is the concept that the constructor creates a partially constructed offspring, which is then left to complete its own construction. The von Neumann model of self-replication envisages that the mother automaton should construct all portions of daughter automatons, without exception and prior to the initiation of such daughters. Partial construction alters the construction relationship between mother and daughter automatons, such that the mother constructs but a portion of the daughter, and upon initiating this portion of the daughter, thereafter retracts from imparting further influence upon the daughter. Instead, the daughter automaton is left to complete its own development. This is to say, means exist by which automatons may develop via the mechanism of a zygote. Self-replicating spacecraft. The idea of an automated spacecraft capable of constructing copies of itself was first proposed in scientific literature in 1974 by Michael A. Arber, but the concept had appeared earlier in science fiction such as the 1967 novel Berserker by Fred Saberhagen of the 1950 novelette trilogy The Voyage of the Space Beagle by A. E. Van Vogt. The first quantitative engineering analysis of a self-replicating spacecraft was published in 1980 by Robert Freitas, in which the non-replicating Project Daedalus design was modified to include all subsystems necessary for self-replication. The design's strategy was to use the probe to deliver a seed factory with a mass of about 443 tons to a distant site, have the seed factory replicate many copies of itself to increase its total manufacturing capacity, and then use the resulting automated industrial complex to construct more probes with a single seed factory on board each.